All right, this is 2018. Number one, we're getting closer to the most current years. National average on this guy was 4.5, 4.5 out of 10. We can find more than 4 points or more than 5 points on this thing. So just pay attention to what you're doing. Watch as we go here. They give us a balanced equation at the top, and then they feed us a little softball to get going. So number 1A says determine the oxidation number of chlorine in that sodium hypochlorite. And so we have sodium hypochlorite here in the equation. Don't be scared because the O and the Cl look backwards from what we're used to. We lots of times would write this NaClO. This is how the structure is drawn, and so it's a little more accurate that way. Sodium is in group 1. Group 1's oxidation numbers are always +1. So we know that. Chlorine and oxygen. Oxygen's usually a -2. It's a -2 here as well. If you're not sure between those, choose the more electronegative one. That's oxygen. And so oxygen's a -2 there. That means chlorine here is a +1 oxidation number. So our oxidation number for chlorine is +1. That's it there. Part B says calculate the number of grams of sodium thiosulfate needed to prepare 100 mils, 0.5 molar sodium sulfate. You get thiosulfates, all right? You get concentration in volume, turn it into moles. You're not sure what to do, turn something into moles. We can find grams per mole. So this is 0.5 molar times the liters. It's 100 mils, so it's 0.1 liters. That gives us 0.05 moles of Na2S2O3. They don't want moles, they want grams. And so moles come down, grams on top. It's 1 mole per, I believe it's 158 grams. That gives us 7.90 grams of Na2S2O3. Make sure you get units on stuff. Units, 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 units. These guys, 5 sig figs here, 3 sig figs there. When in doubt, 3 sig figs. But 3 is the least of those. That's the proper number of sig figs for that particular problem. Then it says, in the experiment, the student uses the solutions in the table below. Perfect. Using the balanced equation for the reaction, determine which one is the limiting reactant. What I recognize right away is the molarities and volumes of all 3 reactants are exactly the same, which means they're equimolar. And so I start there. Because they're equimolar, NaOCl will be the limiting reactant. The reaction uses, and then talk about the stoichiometry from the equation. 4 NaOCl's to react with 2 NaOH's and 1 Na2S2O3. They're equimolar. NaOCl will be the limiting reactant. And that's good. Answer their question. The reaction uses 4 NaOCl's to react with 2 sodium hydroxides and 1 of those sodium thiosulfates. That's it. Good. On part C. On part D, they give you a little graph. It says all those solutions are mixed together. I think they're all aqueous in that reaction. We'll look again in a second. But all those solutions are combined in an insulated calorimeter. Temperature of the reaction is monitored to show the following. We started at 20 degrees Celsius. We went up to somewhere in between 32 and 33. If it's in between there, 32.5 is good. These guys are accurate to the 10th place, so your measurement needs to be accurate to the 10th place here as well. Part D says according to the graph, what is the temperature change of the mixture? It's a softball question as long as you don't goof significant figures. So 32.5 minus 20.0 equals, I got 12.5 degrees Celsius for my temperature. That's my temperature change. That's what they asked for in Part D. What's the temperature change of the reaction mixture? Simple enough question, as long as you be careful, make sure you go to the tenths place since their thermometer is going to the tenths place. Then it says the mass of the reaction mixture inside the calorimeter is 15.21. And by the way, on this one above, they take 12.3, 12.2, up to 12.8 probably. Just recently I've heard several times, if it's in between values like that, that's a half, right? Don't point for it or get too excited, call it a half. If it's close to or on the line, call it a 0. But that guess digit, half is good for a guess digit, but they give you a little leeway either way. Part E says mass reaction inside the calorimeter gives you 15 grams of it. Calculate the magnitude of the heat energy in joules. That's important. Assume the specific heat is this. They give us a specific heat. Second I see specific heat, I'm doing Q equals MC delta T. And then I'm hoping I've got everything I need. Q is the heat energy that's going to be released. They give us a mass, 15.21 grams of the solution. That mixture they give us the constant for, 3.94 joules over grams degrees Celsius. I tell you guys all the time, be careful those units. Grams, make sure that it matches with grams and that constant, and that one of them's not kilograms. Be careful, they want joules. This one happens to give it to us in joules, which is nice of them, but sometimes they'll give it to us in kilojoules, so be careful there. And then times the change in temperature we just found, 12.5 degrees Celsius. That's what our setup looks like. And Q in joules, like they asked, is 749 joules of heat. That's how much heat is given off by that thing. You can put joules released, that's fine. Good, part 2 of that. And this is tough, a little bit tough here. It says using the balanced equation. There's a reason you're using the balanced equation. In your answer to part C, calculate the value of the enthalpy change in kilojoules per mole. So we need to turn that joules into kilojoules per mole. It says we're reacting from part C, right? So part C, we figured out that they're all equal in moles. No, we didn't actually calculate their moles. We're going to have to here because we want kilojoules per mole. And so that limiting reactant determines the heat. So we got 0.5 molar times the volume. And so for E2, we're going to have 0.5 molar times the 0.005 liters from those milliliters. And that gives us 0.0025 moles of the sodium hypochlorite. They want kilojoules per mole of reaction. And so here we go. I've got joules. And so I'm going to change it to kilojoules. You don't have to show the conversion to change it to kilojoules. I just did that, 0.749 kilojoules divided by 0.0025 moles of the NaOCl. And when I do that, I got 300 kilojoules per mole of NaOCl. That's per 1 mole. Here's the tricky part. Here's why they said using the balanced equation, because that's a mole of NaOCl. We need moles of reaction. And so moles of NaOCl in that reaction, for that reaction there were 4 moles of NaOCl. That's tough. That guy equals then 1200 kilojoules per mole of reaction. Be careful here too. Look at, they said include the appropriate algebraic sign. You know what they're telling you? They're telling you the sign is negative for that thing, is what they're screaming at you. That's a negative 1200 kilojoules per mole. That's my delta H for that guy. Got it? Don't forget the negative sign. Perfect. That's E2. We got a couple little quick hitters to finish up. Letter F says the student repeats the experiment. This time they double the volume of the stuff in the table. It says the magnitude of the enthalpy change in kilojoules per mole reaction is exactly the same as the first reaction. Explain this result. We doubled the moles of the hypochlorite. So we would double the energy released. Therefore, the kilojoule per mole ratio would be the same. If you double the amount of moles that are reacting, you're going to double the amount of energy, right? But this is kilojoules per 1 mole, yes? And so if it's the same ratio, it's still going to be the same number of kilojoules per mole, right? We would double the top number, double the bottom number, gives us the same delta H. That's what that says in part F. And then part G, our last one here, says write the balanced net ionic equation for the given reaction. This is crazy, but it's all back to that original reaction that we have here. They want the net ionic equation. Aqueous things split apart, and we look for spectators here. That sodium is a spectator. Sodium's aqueous on both sides of the reaction, so every one of these sodiums is a spectator. There's nothing else in there that is the same on the reactant and the product side. Water stays because water is a pure liquid, and so it doesn't get canceled from the net ionic equation. And so we are just writing what we got once all the sodiums are out of there. So this looks like this. Thiosulfate, S2O3 with a -2 charge. Plus, how many OCLs? 4 of those hypochlorites. Plus 2 of those hydroxides. Go to form. We got 2 sulfates here. Plus 4 of those chlorides, the -1, plus that water. I always like to look, once I've written a net ionic equation, make sure the charges total up the same on both sides. So there's -6 minus 2 more is -8. There's -4, and -4 more, -8. That's it. That's my net ionic equation. You just got to get rid of those sodium spectator ions for the last point on that question. They could have asked that question first thing in that particular problem. There it is, number 1 on 2018. It's doable. Walk yourself back through it. Make sure you're good. Talk to you soon.